So welcome once again to everybody to this acoustic webinar. Today we will see together how simulation helps to improve the vibro-acoustic performances of space structures. I will begin this presentation with a slight introduction to the current space problematics and trends. We will see that many of these problematics are vibro-acoustic challenges that can be solved by Actran. In particular, I will present you the new wizard dedicated to space application. We'll then talk about an innovative and efficient approach to evaluate the influence of design uncertainties, that is, the non-parametric variability method. But let's talk about the context around the aerospace industry. The aerospace industry is very diverse, with a multitude of commercial, industrial, and military applications. More and more powerful rockets are required. They are used to reach longer distance or higher lift capacity. And because they are more and more powerful, the sound pressure levels generated at the launch are also getting higher around the vehicle. Because of that, crew safety is crucial. The very loud sound generated at liftoff can cause permanent body damages to crew members. But it's not only to human body that sound can cause damage. Louder the sound, higher the risk of damages to the launcher structure or the high technology component embarked. Indeed, the intense acoustic field submit the structure to high vibration levels, structure fatigue, and payload stress. The main challenges of the aerospace industry are therefore to model the vibro-acoustic problems and predict the vibration levels of structures submitted to intense pressure loads. In this context, simulation is the required tool for prediction, optimization, and cost reduction, so that for a given design cycle, you can efficiently iterate before the prototype building. Prototype that can now be the right one at the first shoot. Actran is a complete vibro-acoustic simulation software made for helping engineers in these tasks. Let's see how it handles the various vibro-acoustic challenges in the space industry. For each type of external noise sources, Actran has an efficient corresponding numerical model. Let's consider one of the first exterior source, that is the acoustic field generated at liftoff due to the engine noise. This excitation can be seen as a broadband and random acoustic pressure. It is equivalent to a diffuse sound field. The second source of vibration is not acoustic this time, but is an aerodynamic load due to the pressure fluctuations along the vehicle surface. These ones come from the small turbulent fluctuation in the boundary layer, which are predicted with the turbulent boundary layer model. Finally, the third type of external source is the structure-bound noise due to the structure vibration and the acoustic transmission. For that purpose, the acoustic insulation performances can be predicted via transmission loss and noise reduction index studies. In addition, the vibration levels and the induced constraint can be predicted and coupled to an acoustic fatigue analysis. But let's go inside the fairing and better understand the situation. The fairing is used to maintain a clean room environment for payload and precision instruments. In particular, it is the location where carry-on components such as satellites are stored. Such components have very fragile parts that are, for instance, antenna or solar panels. Due to the different acoustic noise sources, a broadband pressure is generated inside the fairing. This broadband pressure is equivalent to a diffuse sound field. In order to correctly and precisely model the behavior of the carry-on component inside the fairing, we do have specific modeling challenges. These challenges are the consideration of the installation effect, also named masking or edges effect, and a correct representation of the acoustic environment and loading, that is a diffuse sound field. The installation effects are related to the complex structure geometry. Because of this geometry, there are external surfaces that are not loaded by the incident acoustic field. To include the masking effect in your simulation, the fluid surrounding the studied object should be modeled. We have seen that the broadband pressure inside the fairing is equivalent to a diffuse sound field. This diffuse sound field excitation is applied along the non-reflecting surface and represented by the superposition of a large number of plane waves with different orientation. The generation of the plane waves is automatically done around the structure and equally spread around the reference sphere. The random character of the excitation is modeled by sampling random phases. The random excitation therefore becomes a combination of different deterministic results for which the phase of the plane waves change. One realization of the random process provides one result, and the PSD values are obtained by summing the square result. The convergence of the PSD therefore depends on the number of samples considered during the Actran computation. PSD levels from experiments can also be used to define excitation levels. I draw your attention on an important point. Only one Actran calculation is needed thanks to the multiple load analysis. The masking effect and broadband pressure modeling are used inside the hybrid method. The hybrid method in Actran relies on intermediate results provided by external tools for modeling the structure. The structure is in modal coordinate system thanks to a first modal extraction analysis that can be performed with Nastran. The structure model and modes are then imported in Actran, and the model is made more complete by including specific acoustic excitation and components. Finally, a hybrid calculation is performed with Actran for a fully coupled vibro-acoustic study, including a structure in the modal coordinate system and acoustic components in the physical coordinate system. Thanks to our automatic and adaptive acoustic components, the exterior fluid is not necessarily meshed by the user. Including meshing tools are indeed available in the graphical user interface and the Actran solver. This methodology has been successfully applied during different studies. One of them was done in collaboration with EADS, where experimental results were compared with numerical one. The study consisted in predicting the vibration levels on the equipment bay of the Ariane 5 vehicle submitted to a diffuse sound field. The equipment bay is the brain of the launcher, and any damage needs to be prevented. A finite element model of the equipment bay structure has been built and submitted to a diffuse sound field. Numerical results were compared with experimental ones, showing excellent correlation over the complete frequency range of interest. Now, please let me present you the new diffuse sound field wizard for aerospace industry. For that purpose, I have selected a satellite antenna, here highlighted in red. The methodology used to study the vibro-acoustic response of this antenna is the hybrid methodology, where Nastran structure model and modes are used to build an Actran model. We will see how the new Actran diffuse sound field wizard ease and speed up the building of the Actran analysis. So when you are in Actran, to open the new wizard, go in the top menu bar in the wizard section and select diffuse sound field wizard. A window opens and welcomes you to the diffuse sound field wizard for aerospace industry. To start building your analysis using the diffuse sound field wizard, simply click on Next. The first stage is the analysis parameters definition. that are the frequency used for your computation and the gravity constant that will be used if you ask solid acceleration in G-unit. So in my case, I will define a linear progression of frequency starting at 20 Hz with a step of 2 Hz and going up to 1000 Hz. Once you have finished to define the first analysis parameters, click Next and proceed to this time the structure mode definition. So in this section, I will provide the mesh of my structure and the corresponding modes that I have already extracted. In my case, I'm using Actran BDF mesh format, and I need to provide a path to the BDF file. Once it's done, Actran is automatically loading the structure mesh in the background. So in addition to this mesh, I will provide also the modes that are in my case stored into an Actran OP2 file, and I will provide a path to this file. I can then select the number of modes I want to consider in my computation. In my case, I do have 323 modes, and I'm applying a global damping, so structural global damping, over all the modes, and I'm using a value of 5%. Once the structure mode definition is done, simply click on Next to move on. Now we are in the acoustic panel definition. As we want to consider the masking effect, we know that we need to model the surrounding fluid around my structure. For that, I need a closed surface around it. So I'm selecting the modeling of masking effect, and I will select the option Create Acoustic Coupling Mesh. I do not have an acoustic mesh already available, and I will create my closed surface around the structure using the Actran VI meshing tools. To do so, I will use the shrink wrap tool, and I will select New in order to create a new closed surface around my structure. When I do that, the wizard lets me the possibility to use the graphical user interface and its meshing tools. I need to select the structure element around which I want to create my closed surface. I need to specify a certain acoustic mesh size. In my case, I'm using a 4 cm element size. And I need to specify a certain distance in between the acoustic and the structure. I will use 1 cm. Once you have finished to define your parameters, you can make an interactive preview of these results. And if it suits your needs, simply click on Create PID and you go back to the wizard. Then we need to define the thickness of the acoustic domain, so the thickness of the surrounding fluid around the structure. We will use a 20 cm thickness. I will keep the material definition as it is because my model is in SI units. And in order to couple the acoustic with the structure, we need to define a gap tolerance value. As we have an acoustic mesh distant from 1 cm of the structure, we need to provide 1 cm gap tolerance value. Then you need to select the structure elements you want to couple with the acoustic. In my case, I will select all the 2D element surfaces. Okay, so now we have finished the acoustic definition and we can proceed to the next step. That is the diffuse sound field excitation definition. In order to model in situ case, we can define a PSD value by table. In my case, I already have a table under text format that will contain all the PSD value as function of the frequency. So I'm selecting table import existing table. The table format in my case is TXT, but you could use CSV as well. And I will select my PSD table. In this table, I do have PSD value for each octave band defined in dB. So I can keep the interpolation octave But in order to tell to Actran that I'm using dB value, I need to provide a reference dB value. That is, in my case, as I'm in SI unit, the typical Pascal value. The convention is quadratic because we are using PSD values. I do not need any band normalization. Now I need to define the sound speed and fluid density. These values will be used to generate the plane waves in order to create the diffuse sound field. As I'm in SI unit, so I will use the typical values for sound speed and fluid density. And finally, remember that we are using a sampling strategy to generate the diffuse sound field. So you need to provide a number of samples, that is by default 13, that is enough in our case, and a certain number of parallels that will be used to create our plane waves around the structure. For you to know, if you forget to define any of the inputs and you want to go on the next stage of your definition, you are blocked by the wizard. The wizard is telling you that some properties are not set and missing values are therefore need to be provided. So in my case, I did not provide any number of parallels, so I will correct this. And now I can move on. So this mechanism is made to be sure that you are not forgetting any of the inputs in your analysis definition. In the final stage, I will define the outputs I need. So in my case, I will define one accelerometer at a certain node. So I already know the node ID of my model. On this node, I will ask the solid acceleration in G units along the normal. And in addition to these accelerometers, I will also specify an element on which I want the stresses. So I provide the ID of my element. Then I ask specifically the solid stress. And I will ask the solid stress using the von Mises formulation on the maximum fiber of my composite. So I finished the different stages of the wizard. I can click on finish. When I do so, I come back to Actran VI, where I see that in my topologies I have the structure that I have defined, the acoustic mesh that has been created, and all the component analysis we have defined, as well as the boundary condition and the post-processing requests. Of course, so this model is ready to be launched, but we can also include additional components if we want. Once you have launched the computation, you can post-process the results using the PLT viewer, where you can plot the von Mises stresses, so on the elements I have specified, or the normal acceleration at my accelerometers. So, at this stage, we have seen that the aerospace domain is a highly demanding industry, requiring specific tools, and more particularly simulation to design efficient structure. Specific modeling challenges need to be overcome, and Actran, thanks to its rich Vibro-Acoustic capabilities, can answer all of them. The new Actran Wizard for aerospace applications offer guidance to engineers in order to easily and efficiently build up a complete Vibro-Acoustic model. But it also provides a boost to experts and experienced users to speed up their operation. The created model can be easily modified and enriched inside Actran VI. Until now, we have seen how deterministic models helps to design space structure and components. We have discovered the new wizard and seen how it helps to create your model. But in order to study models' robustness and consider uncertainties in your computation, additional tools are needed. This is why we are pleased to introduce the non-parametric variability method. The best way to describe this method is by analyzing its name. Let's focus in the first time on the term variability. The variability is the sum of two characteristics, the sensitivity and the uncertainty. The sensitivity is a well-known characteristic that can be seen as the ability to react to a certain change. But when we talk about uncertainty, the interesting question is, where is uncertainty? Indeed, there are several sources of uncertainty. If we have a look at a satellite, one of the first sources of uncertainty is in manufacturing. The first illustration of uncertainty in manufacturing was done by Compella and Bernhardt in 1996, when they compared several frequency response functions of one vehicle to 57 identical vehicles. By making the comparison of the frequency response function, they could see that differences were coming first from the environment, so in the way the frequency response function was measured, but most of the differences were in between the reference vehicle and the fleet, showing the impact of manufacturing in uncertainty. Of course, for your application, manufacturing uncertainty will not be as important thanks to the high precision tools that are used. But uncertainty also occurs in the transition in between reality and virtuality. Indeed, during the virtual model building process, a first source of uncertainty will be the mathematical modeling. It can be, for instance, the choice of the governing equations used to describe complex composite solar panels. In addition, the choice of numerical simulation technique might also lead to uncertainty. It is, for instance, well known that boundary element methods cannot consider strong free structure coupling. The non-parametric term derives from the way variability is introduced in a numerical model. Indeed, instead of making the characterization of each local source of uncertainty, we go for a global approach, where variability is added at a global level. So what does it mean? Well, we start from a nominal model, that is your current model, described by its system in modal coordinates, and we build based on it a random model. To do so, random matrices of stiffness, mass, and damping are created using a sampling strategy. Knowing what is the method, let's see why do we need it, and for that let's have a look at a typical response indicator in the frequency domain. In particular, let's observe the way this response varies with the frequency. We can clearly highlight three main regions: the low frequency range, the mid frequency range, and the high frequency range. Now, in terms of model characteristics, at low frequency, we are typically looking at local response thanks to local indicators. So for instance, the acceleration at one particular point on a structure. In addition to that, we do have a small number of global modes. On the opposite side, at the high frequency, we are used to look at system level response thanks to energetic indicators. For instance, the average vibration levels on a plate. And in addition to that, we do have a large number of local modes. So when going from low to high frequency and passing to the mid frequency range, local modes effects are becoming more important. By nature, these modes are sensitive to the modal details, material parameters, and discrete scheme. So the sum of sensitivity and uncertainty is increasing the variability of your model. In order to be able to consider the variability on your model, specific tools are needed that are statistical averaging tool. And this is why we have introduced the non-parametric variability method in Actran. On a numerical point of view, the NPVM method is based on a Monte Carlo simulation algorithm. So it consists in 3 steps. First, samples are generated for each matrices to create the random character of the model. For each of the samples, the response is computed. And finally, the samples results are combined through statistical operations. The results of this method are of 2 kinds. You can access the mean response over the samples. This mean value will be different than the nominal response obtained without using NPVM method. But you can also access confidence interval of the results, allowing you to assess the robustness of the model. Because we are using a Monte Carlo process, the cost of the computation is significantly reduced. This method is under development by universities since 15 years and has been applied on industrial application by Mr. Gagliardini at PSA. This new tool has been recently applied on industrial model of Airbus Safran launchers. The similar hybrid methodology has been used to compute the pressure field loading the structure, starting from the Nastran structure model and mode through a Vibro-Acoustic simulation in Actran. Different result types were studied. First, the convergence in terms of Monte Carlo samples was done. And secondly, the impact of variability level on indicators such as vibration levels or injected kinetic energy was performed. As expected, the average nominal model response, in green in the bottom picture, is different than the 2 NPVM ones. This difference depends on the variability level, showing the impact of variability on final response. At this stage, we've seen what is the NPVM method. It's a non-deterministic method allowing you to study the robustness of vibro-acoustic models in the low and mid-frequency range. This method is based on your existing model already available. And the characterization of the uncertainty is done through a single and few set of global parameters. You do have access to dedicated graphical post-processing functions, allowing you to plot mean response maps and confidence intervals. And because we are using Monte Carlo process, the efficiency of the computation is ensured. Thanks to this method, vibro-acoustic analysis in mid-frequency range is now practicable for industrial cases. You can now characterize the uncertainty during the early design phases of your project, but also analyze the robustness of the model during the validation phase. So, during this webinar, we have seen that the context around aerospace industry requires to be able to prevent any body or structure damages. For that, being able to predict behavior is an asset. Actran and its rich vibro-acoustic library offers all the tools you need to answer your needs and help you in your work. Specifically, the new wizard dedicated to aerospace industry will help new engineers to set up their model and will offer a boost to experienced users in their day-to-day work. In addition, with the help of the non-parametric variability method, it will now be possible to consider uncertainty at the very first design phases, but also assess the robustness of the models at the end of the validation process. All the required tools to improve vibro-acoustic performances and eliminate failures of space structure are now available. Would you have any questions? Please do not hesitate to contact the support at support@fft.be.